All right, today we're going to dive into a paper that honestly kind of changes the game for how we build intelligent AI. It's called ReAct, and it's all about this really cool idea of teaching AI models to not just think about a problem, but to actually go out and do something about it, and to do both of those things together in a loop that looks a lot like how we humans operate. We're in this very weird moment with AI, right? On one hand, you've got these large language models, these LLMs, that can whip up a poem that sounds like Shakespeare or write some pretty amazing code. But then you ask it a seemingly simple question that requires a few steps to figure out, and it just falls apart. It's this bizarre contradiction, and it's what we're calling the AI paradox. So that's the big question, isn't it? How do we get past this? How do we build an AI that's not just, creatively smart, but is also grounded in facts? One that's actually reliable and trustworthy. That's the puzzle that researchers are really trying to solve right now. Okay, so to really get the solution that ReAct proposes, we first have to break down the problem with how these models currently think. It's a method that's, well, kind of genius in its own way, but it's a genius with a pretty serious flaw. That method is called chain of thought, and the idea is pretty simple. You just ask the model to think out loud, to show its work step by step before spitting out an answer. And look, it was a huge step forward, but it has this one giant weakness. It's all happening inside a black box. The AI is basically just talking to itself, using only the knowledge it was trained on, with absolutely no way to check if what it's saying is actually true in the real world. And when you're just thinking in a vacuum like that, two big problems pop up. The paper calls them out specifically. First is fact hallucination, which is a fancy way of saying the model just makes stuff up that sounds right. And the second is error propagation. This is where one tiny little mistake at the beginning of its thought process just snowballs and gets bigger and bigger until the final answer is completely wrong. Now, on the complete other end of the spectrum, you have what you could call act-only models. These things are designed to take action, like searching a website or moving around in a game. But they've got the opposite problem. They can do stuff, but they can't really reason or plan. They're just doing it without thinking, which means they can get tripped up and stuck really easily. So if just thinking doesn't work and just acting doesn't work, what's left? Well, this is where the researchers behind ReAct did something really smart. They took a step back and looked at the best problem solver around, us, the human brain. The paper uses this fantastic analogy, cooking. Think about it. When you're making dinner, you don't just blindly follow a recipe. You're in this constant loop. You think, okay, gotta chop the onions. Then you act. You grab a knife and chop them. Then you observe, I'm out of garlic. So you think again. No big deal, I'll use garlic powder instead. It's this beautiful, seamless dance between thinking and doing. And that's it. That's the light bulb moment. What if we could get an AI to stop being one or the other, just a thinker or just a doer, and instead teach it to weave reasoning and acting together, just like we do? And that, right there, is the core of ReAct. It's a new way of building these AI agents that's based on a really simple but incredibly powerful loop. Think, act, and observe. So here's how it works. First, the model has a thought. It literally writes out, okay, to solve this, I think I need to do X. Based on that thought, it performs an action, like searching for something on Wikipedia. And then, this is the key part. It gets back an observation. It sees the result of its action. And that new information feeds right back into its next thought, and the whole cycle just keeps repeating until it solves the problem. So let's see what this actually looks like. The paper has this great example. The question is basically, besides the Apple remote, what else can control the software it was made for? The old chain of thought model thinks its way through, and then confidently announces the answer is the iPhone and iPad, which is completely, totally wrong. It just hallucinated it. The act-only model doesn't do much better. It tries a search, but the search term it uses doesn't work. And because it can't reason about that failure, it just hits a wall. It doesn't know what to do next, so it just gives up. But now, check out ReAct. Its first thought is, I should probably search for Apple remote. It does, and the observation comes back telling it about a program called Front Row. So its next thought is, okay, now I need to search for Front Row. That search fails. But unlike the act-only model, it can think about that failure. Its third thought is, maybe I should search for Front Row software to be more specific. Boom, that action works, it finds the right information, and it gets the correct answer. It's dynamic, it's flexible, and it actually works. All right, so the theory is solid, and that example is pretty convincing. But does this actually hold up under pressure? does it work when you really test it? Well, let's look at the numbers and see how ReAct stacks up against other methods. They put it through the ringer on these tough benchmarks. One is called Elfworld, which is this complex text-based game where an AI has to navigate a simulated house and do things like go find the pepper shaker and put it in the desk drawer. Tasks that require some serious planning and common sense. And the results, they are just wild. In Elfworld, ReAct pulled off a 71% success rate. The Act-only model, using the exact same tools but without the thinking steps, only got 45%. And get this, Butler, a specialized AI that was trained on over 100,000 examples just for this game, it only scored 37%. Let me just put that in perspective. ReAct, after being shown just a handful of examples, got a 34 percentage point improvement over the previous best method. That's not a small jump. That is a massive, massive leap forward. So, okay, this is way more than just getting a better score on a leaderboard. The ReAct framework really starts to change our relationship with AI. It's pushing us toward a future where we can actually have more trust and, crucially, more control. So here's the real advantage. Because ReAct is always checking its thoughts against real-world information, it cuts way down on that hallucination problem. And because you can literally read its train of thought, it's so much easier to understand and trust. You can see why it did what it did. And that opens the door to something totally new. Humans and AI working together in real time. Just look at this example from the paper. The AI is looking for a keychain and gets a little confused, thinking it's probably in a dresser. But because its thought is written out for us to see, a person can literally go in and edit that thought, correcting the AI and telling it a better place to look. I mean, think about how profound that is. We're not just giving commands and hoping the AI gets it right anymore. We can now step into its reasoning process and guide it, correct its course. We can collaborate with it. This is a whole new way of thinking about human-AI teams. So when you put it all together, where does this leave us? ReAct doesn't just feel like another small improvement. It really feels like a foundational building block for a whole new type of AI. And it leaves us with a really big question to chew on. By weaving together the ability to reason and the ability to act, we're not just building better chatbots, we're building the first prototypes of true AI agents. So the real question becomes, what happens when these agents can reliably think and do, not just in a game, but out here, with us in the real world?